My guest today is Professor Zhirong Huang, who is Professor of Photon Sciences, Particle Physics and Astrophysics at Stanford University and the SLAC National Accelerator Lab. His research focuses on accelerators and X-ray free electron lasers. Welcome, Zhirong.
Hi, yeah, nice to have me here.
Yeah, so thanks for doing this. So we have a couple of technical papers that we want to get to, but before we do that, I want to sort of set the context for our conversation. We're going to talk about X-ray free electron lasers, but I want to rewind time a little bit, go all the way back to X-rays. So X-rays have been with us for about 100, 120 years now.
Yeah, more than 100 years, I believe. Starting from Röntgen, right? Yeah.
Right. And so, so what's the, if you kind of look at the last 100 years, and if you can take us through from the X-ray invention to what we are currently doing, and the connection to the X-ray free electron laser, what have been sort of the biggest step function changes during the last 100 years in this field?
Yeah. Okay. Yeah, I can try to give my perspectives. Of course, I think X-ray was discovered in 1895-ish by Röntgen, and it was immediately a sensation because he shined X-ray on his wife's finger with a ring, which is one of the first images when you talk about X-ray. That's one of the first images people pops up. Yeah, and they immediately find the medical application, but also scientific applications. Not long after that, there's a work by Bragg, father and son Bragg, on Bragg law, and the work by Lowy on understanding what happens if you shine X-rays on crystals, which give the name, the field actually, X-ray diffraction. I'm talking about scientific. I will not emphasize on the medical field, which I think, as you know, when you go to your dentist, you need to get X-rays. On the scientific side, so the X-ray source has always been the so-called X-ray tubes, very similar to what you use in the dentist's office. That has been, I would say, with us as a state-of-art X-ray source for probably 50 years. My number may not be exact, but that also, the other, in terms of X-ray diffraction, another famous picture is the one took by Rosalind Frankfurt on the DNA double helix structure. And that was actually taken, I forgot the exact year, but
1950, I think.
Yeah, it's around that time. And that was taken with X-ray tube in the lab. But from there, Watson and Crick deduced the X-ray, from the X-ray picture, deduced the DNA double helix structure. Of course, that was one of the biggest discovery of the 20th century. And so people definitely realize X-ray diffraction a very useful tool for understanding atomic and molecular structures. And there also need to have better X-ray sources. I think in terms of X-ray source development, the next major milestone, I would say, is the discovery of synchrotron radiation, where basically people find when especially for using particle accelerator, they accelerate and store, say, electron beam at relativistic energy. Those electron beam, when they're being banded in, say, circular trajectory, they yield radiation to synchrotron radiation, and that was initially as just a byproduct of the high energy accelerator, but eventually people find in the I would say in the 70s that can be a standalone, very bright radiation source, especially in the X-ray regime, and
Was
that's
the,
where. Go
what
ahead.
was the first synchrotron at Stanford?
Uh, the the first synchrotron was no, the synchrotron was developed earlier. I think the first observation of synchrotron radiation was done at General Electric, at the company. But the first scientific, I would say one of the first. I don't know exactly is the first. One of the first scientific application of using synchrotron radiation is at Stanford, using a storage drain we call the SPEAR. It's a high energy collider at the time for the actually very famous for the in the 1970s for the discovery of J-side particles, and but it was also used parasitically for synchrotron radiation research. So that was done at the 1970s at the Stanford Synchrotron Radiation Lab.
So synchrotron is an accelerator. The X-rays is, like you say, it's sort of a side effect, right? It is, as you operate the synchrotron, you get X-rays from it, and you could then utilize that for a variety of experiments. But there is sort of a limit to the intensity of X-rays you can get from it, right? Is that the issue?
Yeah. So this was, in terms of X-ray, say accelerator-based X-ray source, evolution of the accelerator-based X-ray source, this was considered a first-generation synchrotron radiation source. Being first generation, it's a parasitic to a high-energy physics machine, and it has limitation in terms of both its flexibility and also the wavelength tunability. Because it's the storage drain was not designed for this purpose. So then I come to the evolution of so-called synchrotron radiation and free electron laser. We went through so-called 4 generations of evolutions. I just mentioned you 1970 was about the first generation. And soon people start building that because it's very useful for material research as well as chemistry and biology. People start developing dedicated synchrotron radiation sources, such as one first developed at Brookhaven called National Synchrotron Radiation NSLS light source. Yeah. So that was 1980, I believe, started dedicated synchrotron radiation with dedicated energy, dedicated beamline design, that's a second generation synchrotron radiation. And the so-called third generation synchrotron radiation is still based on storage drain architecture. However, people use something called the insertion device, which is a sequence of bending magnet, but alternating direction, and they form so-called undulator and wiggler. So instead of bending the electron in a pure circular geometry, it bends the electron up and down, or left and right. So it wiggles through the trajectory, and that yields much more intense and more collimated X-rays. And that's called a third generation synchrotron radiation source.
Right. So one reason we want this is it's really to measure very micro structures, right? So the smaller you want to measure, the smaller the wavelength of the radiation that you need to use. So that's why we go to X-rays, right?
Right. So yeah, that's right. Maybe I should say a few words. Yeah, X-rays for the broader audience. X-ray is just one particular wavelength range in the electromagnetic radiation spectrum. The long wavelengths can go from microwave, radio wave that we're for communication, to visible that we can see, to shorter wavelengths, even shorter than visible is ultraviolet and the extreme ultraviolet. And after that, we talk about soft X-ray, typically in the range of 1 to 10 nanometer wavelength range. Or, in photon, we talk about, as light, both particles and wave. We also talk about their energy, photon energy, from say 1 keV, 100 eV. That's a soft X-ray. And then we talk about hard X-ray, which is has a wavelength of angstrom, 10 to the minus 10 meter. And those X-rays are particularly interesting because their wavelength is about the same size atomic spacing. So they are very suitable for probing atomic structure, for example. So when I talk about X-ray, I would include both soft X-ray, like a 1 keV or 1 nanometer range, to hard X-ray to 10 or tens of keV, or angstrom or sub-angstrom. So it's still relatively broad range, yeah, of the wavelengths.
So hard X-rays are even shorter wavelengths. So 10 to the power minus 10 meters.
Yeah, that's yeah. The technical term is 1 angstrom. Yes.
1 angstrom. And so we were sort of just like the Moore's law. We were sort of moving up this curve in terms of getting shorter and shorter wavelength. And the shorter you get the wavelength, the more. Is there another measure such as brightness?
Yeah, right. So we say you're interested in say hard X-ray at 1 angstrom. So we're not, in this case, we are not moving the wavelengths. We can also talk about moving to shorter wavelength. Let's just say we're staying at one particular wavelength, say 1 angstrom. And the typical figure of merit is for any light source is what we call brightness. I think in other countries they call brilliance. It's basically a measure of how bright the light source should be. If you think about it, you're in a room, you have, say outside is dark, you have a light bulb, so your room is light. But then you want to give a talk, you shine your laser pointer onto a screen, people can easily see the laser pointer. Why is that? It's not because the average power of the laser pointer is larger than the light bulb. In fact, the light bulb has much, in terms of average power consumption and the emission, it's much better than the laser pointer. What's good about laser pointer is its brightness. It's very collimated. The photons are very concentrated in a small spot and a single color. That's mathematical term for that is the brightness. So we say the laser pointer is brighter than the light bulb, right? So if by the same argument, we use this brightness to define the quality the quality of the light sources. And when we talk about the evolution from say X-ray tube to synchrotron radiation, first, second, third generation, which I'll come to the fourth generation later, is in terms of brightness evolution. So people plot this kind of very similar to Moore's law. The vertical axis is the brightness and the horizontal axis is the year. For the first 50 years, we are basically stuck with after the discovery of X-rays, we're kind of stuck with the X-ray tube for 50 years. And then the first generation, there's a jump in terms of brightness. Second generation, another jump. When we say a jump, it's not a factor of 2 or 3 jump. It's a factor of, it's a 2 or 3 order of magnitude jump. So usually those are plotted in the log scale, just like a Moore's law. And the third generation insertion using this undulator insertion device, it's another three factor, it's a 3 order magnitude jump. So this is the sort of what we typically describe the source in terms of their color, which is wavelength, which is photon energy, and in terms of brightness, which means, just like you think about the brightness of a laser pointer versus a light bulb.
So I want to go to one of your earlier papers from 2006, fully coherent X-ray pulses from a regenerative amplifier free electron laser. So you said we propose to analyze a regenerative amplifier free electron laser, FEL, to produce fully coherent hard X-ray pulses. The method makes use of narrow bandwidth Bragg crystals to form an X-ray feedback loop around a relatively short undulator. So you talked about hard X-ray pulses. So what is so special about this free electron laser?
Okay, yeah.
Calling it that, by the way.
Yeah,
But
yeah, yeah. What is that? Yes. Okay. Yeah. So before I talk about the main paper and other papers, you have in mind, let me also introduce the concept of free electron lasers. So far, I only talk about the synchrotron radiation, which is whenever this phenomenon doesn't depend on it's a single electron or it's many electrons. Basically, electrons just emit independently, and you add up intensity instead of that's all basically because they're emitted in an incoherent fashion. So you just add up the intensity. So the more electron, of course, helps because you have a higher intensity. Uh, yeah, so that's the first three generation of the X-ray accelerator-based X-ray sources. Now I want to introduce the free electron laser, which is, again, as you can imagine, another big jump in this so-called Moore law plot. But this jump comes from mainly the electrons start to cooperate. The electrons start to interact each other, and then they actually cooperate with each other to emit the radiation much more intense, much more coherent. And now we're talking about, if you know your fundamental physics, because all this radiation of waves, we're adding the wave amplitude in a coherent way, so the intensity does not just scale with number of electrons, but scale with number of electrons squared. So you add up the radiation field amplitude, and that scale linearly with the number of electrons, but the intensity is scale like a square of the number of electrons. And the number of electrons is usually very big, so that's why the free electron laser is another jump into this domain of coherence and brightness.
so that's the two major differences. One is coherence, and the other is number of electrons in the process, right? So why are we using electrons here? Is it because we can accelerate that closer to the speed of light?
Yeah, okay. Yeah, so let me back off that. I mean, people ask why use there's three words, right? Free electron lasers. I mean, I told you electrons are easy to radiate because they're relatively light. You can easily bend them, manipulate them. They're easy to radiate. And secondly, why free? The name free comes from a typical laser used a typical laser you're familiar with use the electronic transition in an atom where the electrons are bounded by atomic states. Those electrons are usually, say, live in a solid or in a gas. They are not free. So in this case, the free means that these electrons are free from any atoms. They're just like an electron we pull out of the metal. Okay, so that's the free and the electron, and the laser part I explained, it has the laser-like property. So why do we do free electron lasers? That's because free electron laser is completely tunable. Unlike any atomic laser, which is depend on the atomic transition, so you have a pretty specific color. And once you select the material, once it's basically fixed at maybe with some tunability, but it's very much fixed at a certain color. But as a free electron laser, they're free from this atomic transition, and they're being accelerated to relativistic speed, and the wavelengths will be, with a relativistic effect, will be Lorentz boosted to shorter wavelengths, to the X-ray wavelengths, and their tunability completely depend on the electron energy. So if we change the electron energy by changing the accelerator, accelerating energy or voltage, we can change or wavelength coverage of the free electron laser, basically arbitrarily, with of course with a cost the basically is limited by the cost. Yeah.
And so the same device could produce variety of types of lasers, different color, different intensity. Sort of turning the knob on the device, you could create precisely a custom sort of laser. Is that the way to?
Right.
Yeah.
Yeah. So because of the tunability, so the free electron laser tends to operate in find their application in places where conventional laser is either basically where conventional laser is hard to do. For example, in the visible wavelengths, there are a lot of conventional lasers. We don't, and also they're much more compact, like laser scanner or laser pointer. So you don't build an accelerator for those. But they're in the early day of free electron laser development, people actually go to longer wavelengths, such as terahertz regime, where is terahertz in case you're not familiar with, it's a wavelength regime again of electromagnetic radiation that's between microwave and visible. So it's longer than visible and shorter than microwave. It's also very hard. There's a famous terahertz gap. It's very hard to find the coherent source there. So free electron laser in the early days was developed to fill in that kind of gap, and also in the far infrared. And what in that case, also the advantage of free electron laser, another advantage I forgot to mention, is not just tunability, but because you are not depending on the material. Your material is free electrons, and they move with relativistic speed. So you don't have material breakdown. So you can have very high power device because the electron beam is intrinsically high power. So there are people developing high power infrared FELs for various research. But that was early days in the 1970s, 1980s of free electron laser development. Later, due to various technology improvement, people in my field realize you actually can build an X-ray free electron laser. And why that's interesting? First of all, we talk already why X-ray was interesting. Why X-ray is interesting because it has the wavelength is suitable for probing atomic and molecular systems. And then if you can build something that's better than synchrotron with a free electron laser-like property, with a better coherence, with n square, n being the number of electrons enhancement, and with a coherence, so you'll get another big jump in terms of this brightness curve. So that's in the 1990 and then 2000, there was a worldwide effort to build that type of device. And at SLAC, we actually have the first hard X-ray free electron laser, and that offers a billion times higher brightness than the third generation light source. And it's not a factor of 10 or something; it's a factor of a billion. So that's a pretty giant step, I'll say. Yeah.
Yeah, I don't know a lot about this, Zhirong, but I was wondering if this falls into the hands of bad people. Could this be weaponized at some level?
Not this type of X-ray free electron laser, because they're very intense, but they're only intense over millions of billions of seconds. It's like it's very much like a very high power optical laser. People talk about even higher intensity, like a petawatt lasers, but they're only petawatt. They're not a petawatt for a second or minutes. They're petawatt for millions of billions of seconds, right? 10 to minus 15 seconds. So we call it a femtosecond, and they're very short and very intense. Okay, so their average, we can get to their average power is not so high, but what I also told you in the early day, in the 1970s and the 1980s, people do develop a much longer wavelengths, say tens of micron, and very high power FELs. And because that was 1970s, 1980s, it was still during the Cold War era. The free electron laser at that time was conceived as some anti-missile laser, was actually part of the Reagan's Star War, initiative, strategic initiative. So that, there were a lot of funding from that era, but now the X-ray free electron lasers are purely used for scientific research, for fundamental research, I would say.
Yeah, so the diffraction patterns, I guess you can go all the way to proteins and structures, atomic structures, those types of things, right? So
yeah.
So that is the application. You talk about here in the paper a narrow bandwidth Bragg crystal. So what's the connection there?
Yeah, maybe I give you some before we get there. I'll give you some more general application of X-ray free electron lasers. The one so I think we all so brilliance is one thing, because that means you can have so many photons in certain focused down to a certain spot and within certain time window. So that's and why so also I told you the other characteristic of this X-ray free electron lasers are, the duration is millions of billions of seconds. Why that's also important? Because when you actually, so one thing is to look at static picture of atoms and molecules. Those you can do with more or less conventional X-ray sources, including, for example, in the DNA structure, we didn't have any synchrotron or FEL, and Rosalind Franklin still was able to get a beautiful diffraction pattern, because the X-ray wavelength was right, and if you have large enough crystal, you can still get those structures. When we talk about, of course, when you go to much higher brightness, and people use that to solve many more protein structures much faster. And I think some statistic like 80% of the protein database structure was solved by X-rays, something like that. And however, what we also want to use with X-ray laser is not just looking at the structures, but look at the, because those atom and the molecule, they're so small, they move at the femtosecond time scale. So we also want to see their motion, to see the chemical reactions, and also to understand chemical reaction. For example, for photosynthesis, this type of fundamental research, that's where X-ray free electron laser will shine. It's not just look at the static function, static structure, but look at the functions, look at chemical reactions. So I just want to mention that.
Yeah, so at some point you can sort of take a movie, right? So you can actually see what might be happening.
That's right. That's exactly the idea. So, and it has been done, with first hard X-ray free electron laser we call the LINAC coherent light source at the SLAC National Accelerator Lab. That was completed in 2009, and after 10 years of running, we have many interesting scientific results, including molecular movies. So so people say there's still something missing. What's missing is the accelerator to fire such a X-ray laser is built on something SLAC used to have. It's from a high energy accelerator, and it was built in the 1960s. It was a conventional room temperature accelerator. So they can fire such an intense pulse, but they fire it only at a very low repetition rate, about 100 hertz, which means 100 shots per second. So each shot is, this super bright, lots of photon in millions of billions of a second. But because of the limitation of this room temperature accelerator, we can only fire them 100 shots per second. And that's already very useful for many scientific research, but not enough for some more demanding challenges.
And these are all linear accelerators, right? That is where, um, and so from a practical perspective, you need this accelerator to produce these things. So any experiment has to be in close proximity to the accelerator for that to work.
Yes. So this is So the configuration usually is a linear accelerator firing many electrons per second and continuously, day and night, except when the machine need to be maintained. And then we send it into this radiator device where the free electron laser action happens, what we call the undulator. And in there, the free electron laser will produce, and then it will be X-ray will be, the electron will be stopped. X-ray will be transported to the experimental area where you can use X-ray optics to switch between several experiments. In the current LCS configuration, we have 7 experimental stations. Depend on, this all, being pre-scheduled, and people have to come to at least have to bring their sample here to do the experiment. But this day, because of the COVID, especially last year due to the COVID, we're getting much better at running remote experiments. So the sample need to be here. But there's of course people on site to help install the experiment, but people can do a lot of experiment remotely.
And the accelerator itself is multi-purpose, right? This is just one of its functions, I would imagine.
Right now because SLAC LINAC is famous for, it's a 2-mile long LINAC linear accelerator built in the 1960s for high energy physics research. And the LCS, the first hard X-ray FEL, we're only using the last 1/3 of the SLAC LINAC for this free electron laser. The middle section are still used for accelerator research. Now the front 1/3, the very beginning 1/3, which is basically a kilometer long, is now in the process of being converted to a high repetition rate X-ray free electron laser we call LINAC Coherent Light Source 2. And the main difference from LSS1, the difference of LSS2 is we are going to replace, we're already on our way to replace this room temperature copper LINAC with a superconducting technology, a superconducting RF LINAC that's made of a pure niobium cavity and operate at a cryogenic temperature. So we can fire up to 1 million electrons per second. So in terms of repetition rate, or how quickly you can accumulate your experimental data, it's a factor of another 10,000 improvement.
And the undulator that you mentioned, those are magnets, right?
Yes.
So are there sort of innovations going on there as well to further pump up the intensity?
Right. Yes. Yeah. So the magnet technology used for LSS1 and 2 are still based on so-called this hybrid undulate hybrid permanent magnet design. You have permanent magnet, you have irons. So they're still I would say this is a workhorse for both third generation synchronous radiation facility and as well as X-ray free electron lasers, because they're mature technology. And in the meanwhile, we're also, together with other partner labs, we're also developing a superconducting undulator technology. Basically, the magnet itself is also a superconductor, and that's still under development. And I would say still in the R&D phase. Hopefully, that can be used later for such a long undulator beamline. Yeah.
So I want to finish up with your recent paper, refractive guide switching, a regenerative-amplifier free electron laser for high peak and average power hard X-rays. So refractive guide switching. So what's the technology there?
Okay, yeah. Okay, yeah, maybe can I talk about both 2006 and this paper together?
Sure,
Yeah,
sure.
so I kind of postponed your previous question, why narrow bandwidth using Bragg reflector? Yeah, so I talked to you about the spatial resolution, uh, by the wavelength angstrom scale, the temporal resolution femtosecond. I didn't say anything about the bandwidth. And it turns out such a device uh, is relatively narrow band, but they're not a fully transform limited. They're not a fully coherent in terms of longitudinal properties. That's just due to this, the electron start with because the reason is electron initially starts uncorrelated, and eventually they build up correlation. But this correlation is not complete. So you do, in that sense, you don't have a fully coherent X-ray source. And they're not fully coherent. The one feature of that is the bandwidth is larger than the Fourier transform limited, which is pretty narrow in our case because the wavelength is so short. So the bandwidth can be on the order of 10. If it's a Fourier transform limited, even for femtosecond X-ray pulse duration, it can be 10 to minus 4, 10 to minus 5, or even 10 to minus 6 relative bandwidth. So far, we don't get that. In the standard X-ray FEL, we're based on this mode called the self-amplified spontaneous emission. We cannot achieve full temporal coherence. So the two papers you mentioned, I will try to explain both of them here. In the 2006 paper, we discussed one method of building a more better coherent X-ray source by using a Bragg crystal to both, first as you know, the crystal, when you apply Bragg law, only certain color get reflected, and that the narrowness of that width of so-called the bandwidth is very narrow. It's typically on the 10 to minus 5 level. So that's the number one thing. When you shine the X-ray onto a Bragg crystal, you get a part of the X-ray got reflected. Only the part that you actually really like, which is within 10 to minus 5 bandwidth. And then also because due to the technology improvement, people can make very perfect crystal with silicon and with diamond. You can have almost the very high reflectivity, 99% reflectivity. So we suggested at that time you can use the Bragg crystal to both filter the X-ray color spectral purity as well as reflected the X-ray, so it interacting with the next X-ray, next electron beam, and by this repetitive interaction, you build up the power. You also narrow the bandwidth. Okay, yeah. Hope this is not too technical. Yeah, but anyway, that was a suggestion at that time. At that time, all we can use, because of the accelerator, in order to X-ray coming back to meet the next electron bunch, we need the so-called this room temperature accelerator to have multiple bunches in there, so you can meet the next bunch. The 100 hertz, which means 100 shots per second, the next shot is just too long. If you calculate the speed, the 10 millisecond times the speed of light, that you just too large cavity. You cannot rely on such a large cavity to build such a thing. So you needed to have multiple bunches in order for the X-ray to come back to meet the next electron bunch. Okay, that was the 2006 paper.
Okay, so at the highest level, Zhirong, let me see if I understand it. So we are looking for sort of a perfect coherence. We don't get it because over time you get correlations and it sort of becomes less pure. And we are using some sort of a filter. That's what the crystal is trying to do, right? To sort of take away the noise, so to speak, and get it to closer and closer to coherence, right? Is that right way to think about it?
Yeah. So I think that's a good, a very good analogy. Yeah, you use a filter, and the crystal acts as a filter. But in this case, it acts more than just a filter. It also acts as a mirror to reflect X-ray back, so you can interact with the next bunch. But what I was trying to say, if you only can have a copper normal conducting accelerator, you cannot put that many bunches so close by. You can put maybe 10 bunches close by. That limits the application. Now jump to 2020, because we're building this LSS2 with much higher repetition rate. I told you, with 1 million shots per second. Now you can conceive to build an X-ray cavity when the X-ray bounce back, it meet the next bunch in the millions bunch, out of the millions bunch. That's so that basically this idea got revisited in 2020, sorry, to think about, now we have this brand new superconducting accelerator driving LSS2. How can we take advantage of this scheme, as well as the development, technology development in Bragg crystal and in the cavity alignment, this kind of thing, to realize a true X-ray laser that's a fully coherent. Yes.
So you say here a perturbed diamond output coupling cavity crystal to produce.
Sorry, this is the last paper, 2020.
Yeah, it's 2020.
Okay.
And so this is, I guess, still in R&D stage, right? It's still.
Yeah. Yeah. So right. So the paper itself is relatively technical. And we basically talk about how the scheme can be applied to LSS2, but also using a particular switching technique, which is termed as a refractive guiding switching, which is probably very technical to get to basically not just building up the power inside the cavity, but switch it out every shot to provide to the users. It's one thing to have lots of power stored in the cavity, and it's another thing to also switch it out. Because if you think about it, the Bragg crystal will reflect all the good X-ray back, but how do you switch it out? So this is the paper trying to address that. But without getting into the too much technical, yes. So we're trying to, this is a concept for fully built regenerative amplifier free electron laser. And in the same time, we're also carrying out our necessary R&Ds to build a prototype cavity. And we actually call this cavity-based free electron laser, because there's another configuration I didn't have chance to talk yet. It's on the so-called X-ray free electron laser oscillator. It's a companion concept suggested by my colleagues at the Argonne National Lab. Basically, you run this cavity as a stable cavity and just run it in an equilibrium configuration as like an oscillator. You have a laser oscillator, you have free electron laser oscillator. Now you say you can also have an X-ray free electron laser oscillator. So these two concepts are pretty complementary, and they all depend on a very stable cavity and with a high reflectivity that's required. So in this joint R&D project with Argonne, so it's an Argonne SLAC, and also we have a collaborator from Spring 8 in Japan. So in this collaboration, we're trying to build a prototype cavity to demonstrate the technology, and also to demonstrate the gain for regenerative amplifier FEL, as well as for the X-ray FEL oscillator, as a stepping stone to build this full facility, which it was outlined in this 2020 paper.
And so I don't know much about this, Zhirong. I'm just there is the coherence problem. So you get to perfect coherence, you get high intensity. But then the more bunches of electrons you put into it, the higher intensity that you're going to get, right? But the more you put into it, the lower your chance of accomplishing high coherence. So technology sort of has to go together in some ways, right? You need more and more electrons and more higher and higher
Yeah.
frequency.
So in a way, you can think about this as think about the typical laser also always have an oscillator, because all we are feeding back is X-rays. The electron just each electron being after interaction is being dumped to an electron dump. So you can think about the coherence is built up because the X-rays has the memory from previous interaction, right? Because we're recirculating X-rays, so the X-ray always remember what happened before. That's where the coherence really builds up. And so in this paper and other paper suggests if you can have very stable X-rays with very long coherence time, which also happen to mean very narrow bandwidth. So I would say that's the way you can, it's in a way, what we're developing, it's very similar to the development of lasers in the early days of laser development. You start from amplified spontaneous emission, and then you build either you build some seed to amplify the process, or you build a mirror cavity system to amplify the process. So laser has a various configuration, such as amplified spontaneous emission, seeded laser, or laser oscillator. And in this case, we're saying now we know how to build an X-ray free electron laser. Let's think about how we can build an X-ray regenerative amplifier free electron laser and X-ray free electron laser oscillator.
Yeah.
So I would think this is a natural step of progression. Yeah.
Right. So in conclusion, Zhirong, so you said that the second, is it called RSS2?
Yeah, right now, the project we are building is called RSS2, yes.
And so when do you expect that to be operational? And when it's operational, where do you think sort of the biggest applications might be?
Okay, yeah, so the RSS2 is actually close to the finishing line. All the hardware should be in place by end of this year, and right now actually subsystems are being commissioned, being tested. Basically, we use the term commissioning, basically means testing. And next year will be our main time, the main period of time to commission the whole system, from the electron source, because there are many technical challenges from, because a very high rep rate electron source is also not easy to do. So from high repetition rate electron source to superconducting LINAC, which is brand new for SLAC, and also the going through the andulators and to the experimental station. That we hope to do next year. And so the next year will be mostly on commissioning. I think operation should start later next year to beyond. That's and this type of scientific facility is it's a facility open to basically to the whole world. People can write proposals, from various fields to write proposals. There's a peer, there's a panels composed of, from peers of each subfield. They review the proposals, and they, then the decision are made to grant their beam times. So it's a very competitive process because there are only about a half dozen such facilities around the world. And the LSS2 will be the first, as I said in my email, will be the first CW continuous wave for X-ray free electron laser. Basically, what we are saying is the accelerator is always on, and the electron just very steadily at a million up to a million shots per second. So this will be very hopefully much more stable than the first generation of X-ray free electron lasers. And it will serve the scientific community for a long time to come.
Yeah, so from an application perspective, so do you see sort of life sciences applications, maybe material sciences? Where do you think they will be sort of the most exciting?
Yeah. I'm glad to try to answer some of that. Yeah, so I'll say, I'm sure there's other people have maybe different perspectives. Maybe I would say there are several areas where we can make our impact. I mentioned the photosynthesis. There are a lot of fundamental processes we don't understand because chemical reaction happens very fast, and we there in the LSS1 era, we already the scientists already solved like a so-called photo system one. They're the molecule responsible for part of the photosynthesis process, and the photo system two molecules are very complicated molecular structures, and there is still a lot to be gained. So if I think I hope with LSS2 we can make further headways into understanding of photosynthesis, which is definitely important, one of the most important processes for life on Earth. And on material science, I think the main application is on this so-called quantum materials, correlated materials, because, for example, high TC superconductors, people still don't understand their mechanism. And this type of X-ray, especially in the soft X-ray regime, it's a perfect probe for electron dynamics in these complex materials, how they interact with spins, orbitals, and you need a very high repetition rate, because the low repetition rate signal is just too weak. You really need high repetition rate in this case.
Do you think in the superconductivity arena to get to higher and higher temperature superconductivity, but if we understand the process better, do you see
it's mostly on the material characterization understanding. It's not this is not try to push to even higher and higher superconducting states. It's try to understand what happened, the underlying physics and chemistry, so it's a characterization of materials. It doesn't have to be, there can be other type of materials for like a magnetic switching, for various semiconductor applications. Definitely. Also, I think for life science, the interesting part is, as I said, the X-ray synchrotrons can solve a lot of molecular structures. Already have done that. But the X-ray Free-Electron lasers have, I would say, at least two advantages. One is because the pulse is so intense. There's a term we call diffraction before destruction. So you don't need a large crystal. You can do this with a tiny crystal, nanocrystals, and you can actually get the picture in single shot before you blow it up, basically. And there are a lot of beautiful images if you search on the web on this type of thing. So that's one advantage. So the one way of using X-ray laser is you can image very small molecules and nanocrystals and maybe single molecules. The other advantage is you can look at the reactions, right? You can look at the dynamics. That's something typically when you do this in say cryo-EM or in an X-ray synchrotron facility, you have to freeze the sample to avoid the radiation damage. Here, you don't care about radiation damage. If it destroys, so what? You get a diffraction picture already. So you can look at the dynamics of the process. So I would say there are a lot of application on that too.
Yeah, it's exciting. Excellent. Yeah, thanks so much for spending time with me, Zhirong.
Okay, yeah, sure. Glad to talk to you.
Thank you.
Yeah, you ask a lot of interesting questions.
Thank you.